Okay. All right. This is just me. We're going to get to talking about race cars as one of the examples later, a little bit later. But first of all, I'm Kelly Gaunt. I have a degree in mechanical engineering from the University of Toronto. Ben asked me to come here and give you some of my thoughts on a career in engineering. And the way I'm going to do that is I'm going to talk about a bit about my time at the Brophy equivalent. I was at a Brophy equivalent in Windsor, Ontario, Canada. Taught by Brazilian priests, so I'm very familiar with the format of your school. I think it's probably one of the best schools in the world to launch you on your career. But I went through all of that, and when I went through my engineering degree at the University of Toronto, I went on to a career in management consulting with Accenture, which you may or may not know about, but it's one of the largest consulting companies in the world. And as one of my hobbies, I race cars. I continue to race cars. So what I'm going to do is go through a bit of my evolution in my career, talk about 4 examples of engineering as it's applied to those situations, talk a bit about technology and its importance as an underlayer to everything that you're going to do, and then kind of summarize with a few points and take some questions. If you've got a burning question throughout this, please ask it, because as I understand what the purpose of this, it's to have people like me give you all of this information and help you make decisions, or at least formulate decisions, on where you're going to go with engineering or in a technology field or something like that. So there's no questions or wrong questions. Anything you want to know, I'm happy, if I've got an answer, I'll give it to you. I went to University of Toronto for mechanical engineering. I graduated way back in 1988. We called it applied science and engineering. We always laughed at the math and physics guys who were off doing, 10 decimal place work, because what we did is we applied physics. So we actually took the information that we had out of class, we went into labs, we applied it, we figured out what the equations meant with physical materials, with stresses, with motion, with fluid mechanics, and we applied that. So we always laughed at the math and physics guys, because they sat there on chalkboards and we went to labs and made stuff work, which was pretty cool. I always liked that. Kind of what you guys are doing right here. I was fortunate enough in my studies to stumble across Ontario Hydro, which is Ontario's the biggest state in Canada, state equivalent to province, and they are one of the biggest nuclear plant provinces in the world. In fact, China buys a lot of our reactors. There's tons of them all over the world. The CANDU reactors are some of the safest in the world. I got to work on those. We'll talk a bit about those. This is a company you may know about, Freeport-McMoRan and Phelps Dodge were 2 of the biggest mining companies in the world. Phelps was a Phoenix-based company, Freeport-McMoRan was in Louisiana. They were one of my biggest clients when I was with Accenture. I could talk about the engineering involved in them and the merger. Accenture was the company I had my career with for 30 years, and it's a global management consulting firm. Talk about the path getting into that, and why that was so important. And you'd wonder, management consultants along with engineers. Well, it's an interesting story there, and we'll talk about it. And then we'll talk a bit about racing and how that applies, and it's a passion and it's fun. Racing is engineering. There's no two ways about it. All you're doing is dealing with the trade-offs in engineering, and you guys do it in your robotics labs, your competitions, and so you do that. And we'll finish with technology as a common thread, and any questions you have as you try to figure out your path throughout engineering. So I'm not going to go through the detailed slides. I'm just going to make comments about these as we go. But let's dive into my time at university to start. So one of the things I would like you to understand about where you're at is you don't know what you don't know. I changed my mind probably 5 times in my university career about what I was going to go do. When I started, it was aerospace engineering. I was hung up on space travel and astronauts and building rockets and things like that. And my uncle worked for Thiokol. You won't know that name, but right around that time that I was in that, I was applying for a job there in the middle of college, and the Challenger blew up. Thiokol made the solid rocket boosters. So my thoughts are, there's not going to be a lot of demand for that for a little while, so I might want to consider something different. And it's an unfortunate engineering accident. We'll talk about those later, but those are the kinds of things that can change your trajectory. I did have the opportunity to work in labs on things like scramjet engines, supersonic combustion ramjet engines, which were very cool. We're using them in space planes now, 25 years later, at hypersonic speeds. We worked on things like the Canada arm for the space shuttle. If you remember that, the arm that stuck out of the belly of the space shuttle, that was made in Canada. We did research on that at a university. And then civil engineering projects like Sky Dome. It was the world's first retractable dome in Toronto. And it's just a huge roof that opens up, air conditioning. I mean, we have them all over now, but at the time it was very unique. So calculating crazy things like wind loads and snow loads and modeling things like that were all very cool labs that we get to do in engineering. So if you're going to a cool engineering program, there's lots of them around the country, around the world. You will get lots of opportunities to work on stuff like that. And if you're engineering oriented, there's no limit to what you can do in that space. But you can take full advantage of any one of your labs. I did get to work on a little bit of nuclear stuff in the lab, but I was fortunate enough to get a summer job at Ontario Hydro. And a professor found me and said, this guy knows a little bit about computers, knows a lot about engineering and math. I need some help building what's called a finite element analysis program to simulate tube sag. So inside a reactor, you have fuel bundles that go through it, and the water goes through the fuel tubes, and these tubes are made out of a titanium alloy, and with neutron bombardment over time, the modulus changes and they sag a little bit. Well, at a certain point in time in a reactor like this, you have to do what's called a retube. So you can't go in there, people can't go in there. So you have robots that go in there and change these tubes out, and you can imagine it costs about $1 billion to do that for a reactor. So it's not cheap. So they want it to last as long as possible. Well, my professor didn't think that they were calculating it right, and we were just getting started with the computing age, if you will. He got me a room full of computers of this size and said, write these programs and figure out if we're right or wrong on this. And it turns out the engineers were wrong, and they had to be retubed a lot sooner, and we were proving it using our analysis, finite element analysis, which you guys probably do today on your iPhones if you do any kind of computer fluid dynamics or any cool simulations. That's the basis of that kind of technology. So that was a really cool way to start my engineering career, but it was also kind of the end of my hardcore engineering career, because that particular company was a crown corporation, a government organization, and they kind of turned me off of engineering, if you will, in the way that they did things. It just wasn't fast-paced enough for me. So at that point, I moved on to what eventually became Accenture, and that was a management consulting firm, and that really allowed me to get to a lot of different clients, one of which was Freeport McMoRan. Anybody know who that is? Freeport McMoRan? Okay. Phelps Dodge, you've heard of them?
Was it Arthur Anderson you started at?
I started at Arthur Anderson, yes. So Arthur Anderson, these guys won't know this, but Arthur Anderson was an accounting firm, and the partners recognized that computers are going to be the way of the future. And so they had a very, very small division of people who were figuring out how to put computers into businesses. And my then current, the partner that hired me, Neil Kidwell, specifically went to the key universities in Canada and said, bring me the best engineers you've got. And I got a call out of the blue from these guys because I was working in nuclear plants, and they said, come visit us and talk to us about a job at Arthur Anderson. And my frat brothers were like, you gotta go, you gotta go. What do I want to do with an accounting firm? I'm not going to do accounting. But I went there and he said, we don't do anything with accounting. What we're going to do is go fix companies. We're going to go to the shop floor. We're going to take technology. We're going to put it in, like you guys are doing in robotics. We're going to figure out how to make stuff go faster through the shop floor, make the company more productive, and use your engineering brain. This was the key that you guys need to, you'll understand when we get to the end of this. I'll talk about filling your toolbox. But your engineering brain is so adept at figuring out how to solve problems, because that's all you'll do for 4 or 5 years when you're in engineering, is figure out how to solve problems. Take that and apply it to business, and you're golden. So all he did was hire engineers to go work in management consulting, and we'd go around and figure out how to solve these business problems. So, yes, Arthur Anderson was the start. Freeport McMoRan Mining is the largest copper and gold mining company in the world, one of them. An example of how the engineers work, and there's engineers everywhere in a company like that, starts with the geology. So, first of all, where is the gold? And It so happens their biggest mine is in Irian Jaya in Indonesia, where they're just chopping the top off a mountain, basically digging it up and getting the gold and copper out of it. But at that scale, it takes an incredible amount of engineering. You can imagine the equipment that has to go into that and the operational efficiency of doing it. So first of all, as the geological engineer, I got to figure out where is the vein. Then the operational and mining engineers have to figure out how to drill, blast, and haul. So they'll put a bunch of holes in the mountain, fill it full of dynamite, they'll blow it up and crumble the rock, and then they'll take big excavating equipment out, and they'll pull all the ore out, and then they'll process it in one of several ways. If it's an oxide or a sulfide, so the oxides basically get smelted, they burn it, and they'll melt the gold and copper out of it, or the sulfides get electrowinning, and they'll pour acid on it, and they'll leach the metals out of it, store it in big pools, and then they use an electrowinning process to basically extract the metals from the liquid. So all of that stuff, that entire process is run by engineers, designed by engineers, operated by engineers, and maintained by engineers. This is one of the biggest things we had to deal with there was the maintenance function. So when you're operating a plant like this, the operators want to get the most they can out of their shift because they get paid by a shift. Well, the maintenance guys don't want the stuff to break because you're already pushing it as hard as it is, and if it breaks, unplanned downtime is the worst thing you can have. So there's always this push-pull between the operators who are trying to get the most and the maintenance guys who want to fix the thing. So a lot of what we did was basically get people to get to a schedule that said, let's optimize your output over a month. So if I have fewer breakdowns, fewer emergencies, I'm going to get more product out by the end of the month than if I just optimize for your scheduled shift and you leave a broken piece of equipment for the next guy. So there's lots of different things that you can do in a place like that, but it's all about technology, it's all about engineering, it's all about optimization. So any industrial company like that will have engineers everywhere. There'll be engineers in finance, there'll be engineers in operation, there'll be in the core part of the beginning of the process. And more often than not, there's an engineer at the top of the company. All the C-suite will be engineering or engineering related. I found that to be true when I went on, if you look at the rest of the companies that I worked at Accenture, I worked mostly with mining and metals, chemical companies like Dow and DuPont, electric utilities like APS here, or Pacific Gas and Electric, or Ontario Hydro, oil and gas companies, Exxon Mobil, those kind of things, British Petroleum, all the big guys around the world. So that was a great opportunity to travel the world, get into the top level of these companies, solve their most difficult problems, and I would have generally on any one of those projects 300 or 400 people, of which a quarter of them were engineers. Another half of them were business analysts, computer science people, and then the remaining quarter would be hardcore technology people that help put in big computer systems. But the engineers and the engineering trained people, the ones with the critical thinking skills, were always the ones setting the direction, setting the tone for what we're trying to do, figuring out what's feasible, what we could make work. And when these guys are spending big money, they do not want to take chances with, is it going to work or is it not going to work? You don't experiment at the $100 million level. You experiment at the $1 million level, but at the $100 million level, it better work. So a lot of that stuff was very, very high pressure, but it was a lot of fun. Some of the most interesting stuff I ever got to do. Let me take a quick pause there and see if this is resonating. You guys are these examples interesting to you? Are they useful? Is there any question on any one of those examples you want to ask? Okay, let's talk about racing a little bit more. So a couple of you guys race. These two guys right here. Anybody else into racing? Watch Formula One this weekend? Yeah. Lando? Or
I watch it. I follow it.
oh, I followed it. Okay. Lando? Yeah. Okay, so racing is probably it's my passion, one of my passions, but it's probably one of the most engineering-oriented activity you'll ever see, because it brings every discipline together, including the operations and strategy, all to a final point. Who's fastest, who's number one. So let's take an example of how you might understand the fidelity of it. On a track that's a couple miles long, I do a lap. Well, here's a story. My first professional race series with Formula Mazda, I'm an engineer. I'm probably 35 years old. I started late in my career. I go out, I do some decent lap times, and I get out of the car and I go to the owner of the team. All right, let's go make these adjustments. And he looked at me and said, "We're not adjusting the car." I said, "Well, why? How am I going to go faster?" He said, "We don't know what we're doing yet." And he laid out this math for me. He said, "Okay, you've just done a 1 minute 40-second lap time. Yep. That's 100 seconds. Yep. Your lap time variance is a second or two between your first and your last lap. It's no good. You need to give me 5 laps in a row, plus or minus a quarter of a second per lap." Hang on a second. Do the math. That's 0.5% variance over 5 laps. Why would you want me to do that? Exactly. So there's a million things you can change in a race car, including the driver, if he's not any good. But if I can't give him a consistent baseline, a consistent set of laps, plus or minus a quarter of a percent per lap, then if they make a change, they don't know whether I had a bad lap or a good lap, or what we did to the car made it faster or slower. So consistency as a driver is one of the most important things you can have in a race car. They won't touch the thing unless they can get you at a consistent level and you're performing at a way that's predictable. Then, to your point, you can start playing with the other variables. Lower the ride height, change the wings, do this, do that. So operating and strategy in a race car is probably one of the most important things when you get to the racetrack. The other things are cool, but much bigger. So, anybody know who Adrian Newey is? Ross Braun. Okay, these are some of the best race car engineers in the world. They get $100 million budgets, $200 million budgets. They get to go build these Formula One race cars, design them from scratch. They have wind tunnels that run around the clock, 24/7, 365. They've always got a model in the wind tunnel. How cool is that? That's in your backyard. You get to play with that every day. But they will build these race cars from scratch, try to meet the regulations, but be slipperier and faster than the other guy, and lighter and more powerful. That's the height of the engineering, but that's not the whole story. Then you've got a team that's got to bring it together and do what we just talked about, which is find the right setup and conditions for the car at that track, at that air temperature, at that adhesion level, with these tires. So all these variables have to come together, and the amount of data that they use to do this is unbelievable. I mean, there's, you guys have seen it in the computer system we just use on the cars that I showed you. They're massive. They measure everything. I can tell you exactly what's happening to a thousandth of a second on our car. And we measure things like sampling the suspension rate at 10,000 times a second. I'll get a graph that tells me what's going on in that suspension system with that sort of sampling frequency. That's at my level, let alone Formula One. They've got data pipes that are this big and hundreds and hundreds of millions of gigabytes of data that come out just from one race. So racing and engineering to me, that's the penultimate opportunity to display your engineering skills. But it gets me now to the next topic, and probably one of the most important ones here is technology as a common thread. So you guys are doing it in the robotics lab, or anybody that's in the robotics lab is already doing it. When I started my career way back when, PCs were not a thing, laptops were not a thing. They were just basically, I had a VIC-20, a Commodore 64, and I was lucky enough going to a Brophy equivalent that my math teacher secured 5 PCs for a computer lab. And he encouraged me because I was mathematically oriented. He said, let's go learn programming. So I learned basic machine language programming and binary programming of these chips. And we took it, I could can tell you that that changed from that level to what you currently see today. That technology curve, I've seen at least 10,000 multiplier in compute power, probably 100,000 or more in compute power, and applicability of the technology in my lifetime. You guys are in for something way bigger than that. I can guarantee you in your lifetime you'll see some of the stuff that I only dreamed about. Probably see fusion energy, the way things are going. You'll definitely see in the next 5 years an incredible AI revolution. You're going to see quantum computing at a commercial scale, which is probably going to fuel some of the AI things. We're still a little ways away from that, but what quantum computing will be to your life is what Moore's law and silicon chips was for my life. So get ready for that, because the stuff you're seeing today, you're going to look back 30 years and go, wow, that was antique. That was crazy, how powerful it was. A room this big full of computers is what I'm holding in my hand right now in my lifetime. You're going to see the same thing or more in your lifetime. So the point here is, don't look at technology and computing as a side thing, as something I need to go study later. It's going to be pervasive throughout your career. Everything you do is going to be everywhere. Yes, sir.
You're talking about the branches of engineering. I was wondering, because as you were talking about, some fields are growing a whole lot, but a lot of fields are shrinking as well. Do you have any recommendations on specific fields that undecided engineers? I know that it's important to learn a little bit about all of them, but is there anything that you think would be valuable to focus on?
Sure. Excellent question. I like to use the analogy of filling your toolbox. About 70% of the content of the School of Engineering at the University of Toronto was common. Only in the last year and a half of your degree did you start to specialize in very specific things, like in my case, fluid mechanics, thermodynamics, rocket propulsion, that sort of thing. But that doesn't matter. And the reason I say that is the partner that hired me told me that all I'm really looking for is for someone who has a full toolbox. I didn't know what he meant by that at first, but he said, if you've gone through any engineering program, I know you've taken all the math, all the physics, chemistries, probably some communication classes, you understand computing and technology and how it applies to these fields. You've got critical thinking skills, you know how to solve problems, you know how to do all of those things. So I would hire a chemical engineer, a mechanical engineer, information technology. I'd hire any of them, because if you've gone through the program, you've got the basic skills, the toolbox full to do whatever you want. So the advice is, find a niche or find a direction that really turns you on, that you're passionate about. For me, it was mechanical and aerospace and nuclear. I really liked that stuff, quantum physics and all that stuff. I really liked it, so studying was not a problem. I loved it. I would get up and I'd read that stuff just for fun. Kind of weird, but so the thing that you're most passionate about is the direction you should go in. You're going to fill your toolbox, and in the last year or two of your university career, you'll probably change your mind 3 or 4 times, but you'll find something in a company that matches to you, that says, not only is my toolbox full, I was doing stuff that I love doing, and now someone wants me to pay me to do more of that. That's probably how it's going to play out. I doubt I didn't. I thought I was going to pick my major and my direction and my company at the beginning of my university career. It doesn't work that way. It doesn't work that way for most people. You usually go through the process, kind of figuring out what you like. You stumble on an opportunity, keep your mind open for those, and then you jump on it. So I wouldn't get too balled up about getting it right or getting it wrong right now. Just think about the concept of filling your toolbox. Make sure you're loving the work that you're doing, and you're taking every opportunity to make the most out of those 4 years. Don't get into too much debt, but take the opportunity to get the most out of those 4 years to get everything you can, and then keep your eyes open. I used to say, prepare yourself to be lucky. What are you talking about? Prepare to be lucky. Well, 90% of people miss the opportunities because they don't know what they're looking for. Right? If you're focused on what you're looking for and trying to find where you want to go, these opportunities will come up and you'll go, hey, I recognize that. That's a door I should probably walk through. Whereas most people just walk right by, they won't even know it. So preparing to be lucky means studying what you want, know what you want, or know what it looks like anyway, or what it might feel like, and then just keep your eyes open for opportunities and prepare yourself to stumble on that thing that you might fall across. That's what happened to me. That's what happened to a lot of people in my life around me as engineers and people in business. So that's how I would recommend you look at it. Don't get caught up on, I got to get into this program, I got to get to this job, I got to get to this, because you don't know what you don't know yet. Your whole world is going to open up as you go through your university career. Other questions? Oh, sorry.
And after too.
Sorry?
And after too. It's not only after
It
university.
never stops. Never
Great.
stops. I did that 20 more times at Accenture. It was such a great company with so many opportunities. I moved around all over the world in all kinds of different clients, and it just never stops. Are we at the end, or?
Yeah, we ran out of time
Okay,
already.
out of time? All right. Okay,